Hello everyone, welcome back to another video. Today we're going to be continuing with more questions on electromagnetism. So this question 1.5 reads, a coil and a magnet can each move horizontally to the left or to the right simultaneously at the same speed. In which of the following will a conventional current be induced in the coil in the direction shown in the diagram when both the magnet and the coil are moving? Okay, so we need to first figure out the direction of the current here. So we look at the arrows. Okay, so the current behind the coil is moving up, but the current in front of the coil is moving down. Right, so in that way it's forming like a loop. Now the easiest way to imagine this is if you think of you holding a glass or a can or something where your fingers are curled around that cylindrical object. Now I've attached a picture here to kind of give us some idea. Now the picture is not in the right orientation because as you can see in the front of the cylinder, the current is moving up. We want the current to go down. So what we need to do is we actually need to rotate it. That matches up with what we want because we want, again, in the front of the cylinder, we want the current to go downward. That's what we're interested in. So for that to happen, there needs to be a south pole on this side and a north pole on that side. Remember that your thumb points in the direction of north. Okay. So now that we have that, we need to think of what kind of situation or what kind of scenario, what kind of movement will give us south and north in that specific in the image that's there. So again, let's think about what happens when the magnet is moving toward this coil. Now, when the magnet moves toward the coil, right, the south end of the magnet is actually moving toward the coil. So this end here. Now you could think of it like this. The coil does not want the magnet to approach it, right? So in other words, the coil will induce a south end. So if the magnet is moving toward the coil is going to create a south end. That's what we want. So we know for sure that the magnet must be moving to the right. So we have option C and option D. Now let's focus on the coil, right? Now if the magnet is stationary, if you move the coil to the left, the coil will do the same thing because the coil again doesn't want the magnet to approach it. Now it doesn't matter which is moving, but if the coil is moving toward the magnet, then the coil will again create a south pole to repel it. So the coil should be moving to the left as well. Not as well. The magnet should be moving to the right and the coil should be moving to the left. So the answer here should be D. Always remember when it comes to this section, when you have a coil and you have a magnet, the coil will always want to repel if the magnet is getting closer, but if the magnet is moving away, the coil will want to attract it. Okay, so that answer is D. Question number 6. A circular wire loop of radius 0.3 meters contains 17 turns. When a bar magnet is pushed perpendicular into the coil, the magnetic field strength due to the magnet is 3 times 10 to the minus 4T. The magnet is pulled out of the solenoid so that the field changes to minus 2 times 10 to the minus 4T in a time of 1.5 seconds as shown in the diagram below. Question 6.1. Calculate the induced EMF. So we go to our EMF equation. E equals minus N delta phi over delta T. Now here it's completely up to you. If you prefer to solve everything all at once, then you absolutely can. But if you prefer to work things out separately, then that's also an option. For this example, let's do it separately. Okay, because remember, we don't have all the quantities. We know N is 17, right? So minus 17 delta phi divided by, and they tell us the time is 1.5. So what we need to work out is this. That's probably why it's worth 5 marks, because you need to do different calculations. So we can calculate delta phi on the side. We can say delta phi is equal to final minus initial. Now we can work out, because we know that phi equals BA cos theta. The area is the same and cos theta is the same. So we can take that out as a factor. Okay, so work out the area. The area of a loop is, area of a circle is pi r squared. So pi times 0.3 squared, and then multiplied by cos. Now let's consider, we need to think about what the angle going to be here. So I can just draw a quick diagram here just to show it to us. They tell us that it's perpendicular. So if the magnet is here, right, and the magnet is moving this way, and you have your, we're looking at this from the side. So here's our loop. We're just looking at just one loop, right? You can see that it's perpendicular, right? The loop and the magnet are perpendicular. But remember, the theta value is the angle that the magnet is making with the normal of the loop. So the normal of the loop is going to be pointing left or right. So that way or that way. So always be careful. You're not going to substitute 90. You're substituting what angle is the normal of the loop making with the magnet. In this case, it's 0 degrees, right? Because you could say pointing in the same direction. So in this case, we're going to say cos of 0. Okay? And then we still have the B values to work with. All right? So open bracket here. Final was -2 times 10 to the minus 4. Then minus 3 times 10 to the minus 4. Now we can put that in our calculator. Let's just check. Pi and then 0.3 squared times cos of 0, and then open bracket -2 times 10 to the minus 4 minus 3 times 10 to the minus 4. We get an answer here of minus 1,41 times 10 to the negative 8. Now we can take this value and substitute it now in our original equation. So minus 17, and then our answer minus 1,41 times 10 to the negative 8 divided by 1,5. So let's check this. So minus 17, then minus 1,41 times 10 to the negative 8 divided by 1,5. And here we get an answer of 1,60 times 10 to the negative 3 volts. Very small voltage. Okay, and that's how we solve it. If you like this video, please consider leaving a like, subscribing, sharing. If there's something specific you'd like me to do or any questions you have, please put it down in the comment section below. Until the next one, bye-bye.